สวัสดีครับท่านผู้ชมผมทรงวุฒิกระแสอินตอนนี้ผมยืนอยู่ที่หน้ามหาวิทยาลัยซิดนีย์นครซิดนีย์ประเทศออสเตรเลียนะครับวันนี้ผมก็อยากจะพาท่านผู้ชมมาดูนวัตกรรมงานวิจัยหรือว่าเทคโนโลยีที่มหาวิทยาลัยนี้มีว่าเขาจะมีความทันสมัยมีความไฮเทคหรือว่ามีเรื่องราวที่น่าสนใจยังไงบ้างตอนแรกผมก็อยากจะนำเสนอเกี่ยวกับเทคโนโลยีที่ภาควิชาวิศวกรรมเครื่องกลของที่นี่นะครับคือว่าจะเป็นสาขาวิชาที่ผมเรียนเองแล้วก็ต่อจากนั้นเนี่ยผมก็จะพาท่านผู้ชมไปดูนวัตกรรมหรือว่าภาควิชาอื่นว่าก็มีงานวิจัยอะไรทางด้านเทคโนโลยีที่น่าสนใจตลอดจนถึงชีวิตการศึกษาของที่นี่แล้วก็ภาพรวมของมหาลัยที่นี่นะครับก็สวัสดีครับท่านผู้ชมผมทรงวุฒิกระแสอินตอนนี้ผมอยู่กับดร.อารีนะครับในห้องหุ่นยนต์โรบอทหรือว่าหุ่นยนต์ควบคุมอัตโนมัติที่มหาวิทยาลัยซิดนีย์ที่นี่ก็จะมีงานค้นคว้าวิจัยเกี่ยวกับพวกหุ่นยนต์แล้วก็สิ่งประดิษฐ์มากมายครับแล้วก็ในห้องนี้ก็จะเป็นห้องแลบที่คิดค้นคว้าแล้วก็ประดิษฐ์พวกหุ่นยนต์เหล่านี้เพื่อใช้งานในประเทศออสเตรเลียแล้ววันนี้ผมก็ทางรายการเราก็พาท่านผู้ชมมาดูไอ้ตัวนี้นะครับผมคิดว่าน่าสนใจมากครับก็เสร็จแล้วก็ยังมีนวัตกรรมหรือว่าสิ่งประดิษฐ์เทคโนโลยีที่น่าสนใจอื่นๆอีกมากมายก็ติดตามชมในรายการอันนี้ได้ครับ
I'm Ali Haidar Gökdoğan, a research fellow at Australian Centre for Field Robotics, and this is the Field Robotics Lab. And what I will show you is a number of different operations we do, or different robots. What we are here is in front of the submersible group, underwater robots. Currently those robots in the field, so I cannot show them, it is somewhere in the ocean. But we can show some of these torpedo-shaped submersible. They actually navigate underwater, as you can see through those photographs. They capture very high-resolution photographs of coral reef, for example. And one of the challenges in underwater is obviously lighting. The other one is navigation. You don't have the GPS. You don't have luxury to have GPS. So there are different techniques such as what we call SLAM, simultaneous localization and map building, and we use those techniques to figure out our position and then use that to navigate from point A to point B. When we are moving that, the submersible collects lots of data, especially imagery data, and those are well available for the scientists to look at what's happening on coral reef, for example. Can you see two yellow tube kind of things? That's actually the submersible. And it can dive around 750 meters or 1,000 meters roughly.
Oh yeah.
And it's really...
You are doing this submarine?
Yes, we have a group in our SCFR. They work on submersible. This is one of our test chamber. We have a group of people, researchers in Australian Centre for Field Robotics. They work on millimeter wave radars. And in order to have millimeter wave radars on open space, you need to have large open space to measure the distances. Here is very special chamber. When you send millimeter wave radars, this particular material, the material itself and the shape, it absorbs the millimeter wave radars. And from millimeter waves perspective, this small room looks like an infinitely large area. So it is, we can perform some radar experiment.
It look like the sound measurement room.
Yeah, similar to sound measurement room. For example, if this was a sound measurement room, when you're inside, all the echoes will be cancelled. Very similar, actually. It's a very good point. Instead of sound waves, which is obviously very long, we are talking about very, very short wavelengths, millimeter wavelengths, which we have the radars and we develop radars, and this is the test chamber for that.
Oh, the test chamber for the radar.
That's right. In our center, as a part of our Australian Centre for Field Robotics, we have another research centre called Rio Tinto Centre for Mine Automation. And one of the purposes of this Rio Tinto Centre for Mine Automation, as its name implies, automate the mining process. This particular vehicle is going to be used at one of the mine sites for the data collection. It's full of electronics, different sensors. We can, a human can drive this as well as we can teleoperate the vehicle. Many people think that the actual automation of the mining of things is just automate the vehicles. Yes, we automate the vehicles as well.
This is the self-driving car. It is a self-driving car.
Yes, there are self-driving cars, but actually automating the vehicles has little contribution in the mining process. The process itself needs to be automated. So we are working on the developing system from the drill process to the final delivery process. We try to automate the process, not only the machines. So the process automation has better economical value than the automation of the vehicles. And this is one of the vehicles, is again equipped here. We have excellent engineers and they put so much. Actually, I can take you inside and show you. So you can see there are lots of racks, and inside is full of computers. And normally on this part, all the computers removed, but this cabinet is actually full of computers when it's operate. And over this vehicle, we have GPS, we have laser sensors, wireless communication equipment, and LiDARs, so many sensors.
And how to
a human driver can drive, as well as we have a special apparatus that when we put that apparatus, we can remotely operate that vehicle without the human on board. Ordinary car, you can jump into a vehicle and start, and actually the teleoperation kit is actually removed at the point. When the teleoperation apparatus is here, there is not enough space for human, and that apparatus actually, you can see this connection joints, so that apparatus is actually attached to the steering wheel through those 3 points, and it just drives. And actually it also uses the same control pedals, so you cannot teleoperate that vehicle. This is one of our electronics assembly area, and we have some facilities to build our own electronic boards and solder and test a number of electronic equipment. Again, here we have some millimeter wave radar units, all developed here. And we have a limited surface mount assembly facility. We can make relatively small cards, and we test it and assemble here. And as you can see, we have a number of test equipment. Maybe that one later on I will show you on another. This is relatively old, one of our old millimeter wave radar units. And this goes in front of a UAV, unmanned aerial vehicle, in such a way that when the UAV actually rolls to the left, this moves the opposite direction, and when UAV changes its pitch angle, it also changes its pitch angle. And while it is flying, that ellipsoid kind of mirror it actually rotates. And then
The radar in the car or the plane?
In plane, in
plane,
unmanned aerial vehicles, UAV. Later on, when we are walking to the other end of the laboratory, I will show you which UAV is carrying. And this is relatively old design. Again, it's designed and built and tested here at Australian Centre for Field Robotics maybe roughly 10 years ago. Okay.
Yeah. Oh, it is interesting. This is an unmanned plane.
Here is this area is reserved for our unmanned aerial vehicles. We have lots of different UAVs, unmanned aerial vehicles. These are airplanes or helicopters that fly by themselves. For example, I can start with that. This is a small scale, what is called J3 Cup. And inside this UAV, obviously, by the way, you cannot see the wings. We remove the wings when we are here. Inside we have autopilots and navigation computers. And underneath this UAV, we have high resolution camera. So when the UAV flies over the area, wherever we want it to fly, it takes so much and very high resolution imagery. And later on, we take those images and then automatically stitch them together, and then we can have very large, very high resolution imagery, similar to Google Earth. That sort of concept, we can have very high resolution imagery of the operational area. One of the application we use this imagery for is in Australia, we are very sensitive to the environment, and we try to detect the native plants versus weeds. The plants that we don't want to grow is called weeds. So this airplane flies over the weedy area, the weed infestations, and takes thousands of photographs. And later on, we use what is called different machine learning techniques, and we use this collected imagery and then run our machine learning techniques to identify the weeds and non-weed plants. So by doing so, we try to create a weed infestation map, and later on the human experts looks at those maps and identify, okay, this is bad plant, this is good plant. And those bad plants, which are weeds, later on, using these helicopters and also the one at your back, on your back, we use those helicopters and then go and then spray those weeds.
How to control this plane from a computer at home?
And actually, not at home. Obviously, this works in the middle of nowhere. It's in the bush. And we have autopilot. Before we actually start playing, we upload our mission plan to autopilot, and airplane flies themselves. And obviously, during the mission, we have ground station, and we can control the airplane action from the ground station.
For the ground station, it is for photography.
Photography, environmental monitoring, basically.
And
for civilian applications, obviously.
Actually, the funding is from government.
Generally, from government. In this part, environmental application from the government and from the farmers, and
And what is the breakthrough and result of this unmanned plane?
Say again, sorry?
What is the breakthrough or the result of this
so
plane?
far, actually,
it's really used in commercial applications or on the market and.
Australian Centre for Field Robotics is not a commercial entity, therefore our interest is not commercial application. Having said that, actually the results, all the research we performed, all our test flight is extraordinarily successful. And actually we did fly these airplanes on a few different locations. One of them is the Queensland, quite a bit, around 2,000 kilometers away from Sydney. We also tested in South Australia. On Queensland, we detected what is called voodoo weeds. Actually, they look like the good trees, but in reality, actually, they are not necessarily good for that particular environment. And we fly over the hundreds of kilometers, and we collect thousands and thousands of photographs. And after that, our PhD students and research fellows process those data, and then very successfully actually identify those weeds. And then we pass this information to local government entities as well as farmers, so that they actually better manage their farms.
Oh, yeah.
Copter. Again, this is also an unmanned aerial vehicle. UAV, this is another UAV, and this box normally contains an imagery unit and with special sensor cameras. As we fly this helicopter, we can collect again so much imagery, and we can have close-up photograph. And when the big airplanes actually collect that and identify the weeds, we can program these helicopters, and they can go and then apply chemicals on those weeds. So it's a full automation. Directing and the management, or spraying the weeds, can be possible through these unmanned air vehicles. I think the good things about this is many people think that the unmanned aerial vehicles is nothing else but for war. And actually we are quite a bit against that concept. So actual unmanned aerial vehicles can be used, and as this example shows, can be used for civilian application for good purpose. We also have this sort of multi-rotor UAVs. These are multi-rotor UAVs. Generally our undergraduate students or master students use this. And when you put the propeller, similar to helicopters, it can fly. And one of the good things is very easy to build, very easy to fly compared to other platforms. One of the disadvantages, they are relatively shorter flight time, but it is very interesting platform to fly. Australia. So when it comes to Australia, many people know what it is. The boomerang.
Boomerang.
Boomerang in Australia almost the same thing. So as you know, when you throw the boomerang, it flies, and then if you throw successfully, it's supposed to return back. And the reason actually boomerang returns back is relatively complex. It is not easy to explain as an ordinary airplane. There are lots of physical, there are lots of physics running on this boomerang, the spin and the air speed, the lift and the rotational spin, all this together actually makes this boomerang return. So in order to characterize a boomerang, you need to be able to repeatedly throw this boomerang in certain initial condition. One of our master students developed this machine, and what this machine does, if you put the boomerang inside this machine, and this actually spins just similar to human arm, and at the very moment when it releases, it also gives another spin to boomerang to rotate like that. So with this machine, you can throw the boomerang very effectively. The reason we try to do this, actually, on our boomerang, we also put electronics inside, and we record all the physical characteristics such as position, rotational velocities, accelerations, the pressure, airflow, all these sort of things, and try to mathematically model how the boomerang flies. So there are lots of actually theoretical works about the boomerang, but there is no experimental, experiments done with the instrumented boomerang. So this reaction machine plus the instrumented boomerang allows us to compare theoretical results with the reality.
Oh, yeah. Wow.
This is one of our famous unmanned aerial vehicle. It is called Brumby Mark III, and it's designed, manufactured here at Australian Centre for Field Robotics. This is very agile platform. It can fly very fast, and then it can maneuver very fast. And this has roughly 3-meter wingspan, and it has a pusher type propeller. So unlike the other airplanes I showed you before, most of the airplanes, the propeller in the front, but here at the back, The reason is that it pushed airplanes. The reason we have the propeller at the back is just because in the front we want to carry some scientific payload. For example, I'll show you one of the millimeter wave radar on the other room, and actually that millimeter wave radar goes into this glass or plastic and nose cone. So when we fly, we can actually look the environment through the radar, or if we want, we can replace that radar with, say, for example, an imaging sensor or laser scanner or whatever you want. So basically this platform is a sensor carrying platform for lots of UAV applications. In addition to those large platforms, we also have small UAVs. Some of them student projects, some of them are built through our collaboration with the other universities. For example, this particular UAV can fly indoor as well as outdoor. It has its own IMU, GPS, camera and telemetry unit. So as it is, you have a platform to fly. And this is another experimental platforms. Actually, it is designed here and then manufactured here. It has special camera system and it can see very large area, and then it try to navigate indoors using vision. Is another helicopter. Again, it is unmanned aerial vehicle. This helicopter is similar to the previous one, but it can also dispose what is called the herbicides. These granules are used for management of weeds. So it can fly over the woody weeds and then drop these herbicides to actually kill those unwanted plants. What you see here is two ground vehicles. These are again some of our robots developed and manufactured here. So one of them is called Mantis, the other one is called Shrimp. So we have a group of researchers actually use these platforms for the various robotics experiments. Some of them, for example, data vision, the cooperative control. As you can see on this platform, we have a number of different sensors. For example, a color camera, an infrared camera, a vertical laser scanner, and horizontal laser scanner, and we have tri-camera, so similar to our eyes, but with two eyes we can feel the depth. In this case, it has three eyes, so it can feel the depth slightly better than us. And on top of it, we have this red camera is a set of cameras that can see 360 degrees all around. And this rotating sensor is called Velodyne. It's not only give you the visual image, but also actually gives you the depth information. So as it spins, it scans 64 channels and it can give you the depth of say walls or peoples or buildings around, so you can get not only the image but 3D information as well. And all these sensors actually sensor data is fed into a set of computer inside the box. We have so many computers, power and the storage space inside the data storage space, and all these data stored and processed on board. And in addition to that, we also have another platform, again a color camera, vertical laser scanner, horizontal laser scanners and infrared imaging system, so it can see through the infrared. As well as on this particular moment, we also have this rotating thing is actually a millimeter wave radar. So basically these platforms are actually a data collection unit for us to perform experiments. And obviously these two ground vehicles can talk to each other, so we can also demonstrate the cooperative control techniques.
Usually the main task of these robots,
Sorry, I couldn't hear that.
the main task of these robots.
And actually one of the main tasks of this robot is to have flexible data collection platform, so we can operate this for security reason. We can use these robots for monitoring the farms, and actually recently they were on some of the farms, apple farms, and actually on orchards. So you can look at the farms and then think about, tell about how good the trees are. So there are so much different application, but basically these are robotics platforms with variety of sensors, so you can collect those data and do whatever you want.